Right, good morning. Welcome to this course on layered no cross-flow reservoirs and rate time analysis. And it will be taught by Mike Fetkovich. Many of you, I think, have read papers that Mike has written over the years. He's now retired from Phillips, but as is on the overhead, he's a Phillips Fellow Emeritus. He's had an illustrious career with Phillips. He's worked extensively on the chalk fields here in Norway and on the sandstone reservoirs as well, from the well tests all the way through the reservoir analysis and the prediction cases. Several studies that have been completed both here in the UK, for instance on Hewitt. Mike worked from at the outset on the unitization of the Hewitt unit and did some excellent work on that that's carried on through the years. And recently in the States with the Hugoton gas field, the work that's been carried on analyzing the layered reservoir with no cross-flow characteristics and its impact on infill drilling, whether or not that's necessary. Mike's here to share with us this morning his experience that he's gained over these years with Phillips. A lot of insights which frankly have not been picked up that readily by the industry, simply due to awareness or whatever. But nonetheless, we have the benefit of his experience, and he's here to share it with us over the next 3 days. And I'd like to warmly welcome Mike to Stavanger, and wish that we all have a very enjoyable and a profitable course over this time. Mike?
You're welcome. I'll let you pass that out. Well, it's a pleasure to be back here in Stavanger. I think the last time I was here was in 1989. And prior to that, I used to come over very frequently. And a lot of the places here and the faces have changed. So I probably don't recognize anybody left here anymore. But I'd like to sort of give well, let's go into this here a little bit. The first part we're going to talk about basic concepts in decline curve analysis, mainly to get you oriented to the layered no crossflow reservoir concepts. And as you can see here, there's a Phillips shield. I retired in the end of June last year. And Phillips had made a new title for me, a Phillips Fellow Emeritus. I never knew what that meant. Emeritus. I thought that was some kind of distinguished professor at a university. And I found out all it means is retired. That's all it means. So I'm retired. They wanted me to be associated yet with Phillips, even though I retired. I still live in Bartlesville. Emeritus means they provide me an office and a telephone and a secretary, what have you, for, I guess, as long as I live, which I hope is a long time. But they've also provided me, since I'm in Bartlesville, asked me to be under contract with them, which I am. It's a yearly thing. Either they decide they don't want me anymore, or I decide I don't want them anymore. But it's a way to ease into retirement. Well, they're separate items, though. The emeritus means I'm going to at least be associated with Phillips for as long as I live. And I guess you're aware they also made available Reservoir Engineering Award that they're going to give annually. And I know that we've had at least a couple nominations here from Stavanger, and a few from the States, and a couple from the UK. You passed out a book here that has, at least the first part, is a copy of all of the overheads that I'm going to show today. And I've got notes on there that you may want to add to yourself, because every time I give it, it's a little different. One thing that I tried to do with this session was to allow more time to try and be more methodical and deliberate about what I'm going to say. Because usually I give this as a Society of Petroleum Engineers seminar in Houston. I've given it in Oklahoma City and Dallas, and it takes a full day. And because I'm on a time crunch, I always kind of go pretty fast. And I really don't want to do that here. I'd like to get it to be slow and methodical, and if you have any questions along the way, ask them if I can give the clarification, and I'd like to take more time on each of the overheads to make sure that I cover everything that I want to cover. And I guess the other aspect here is we've got a video camera here. I hope it doesn't inhibit me. I'm going to eliminate all the jokes because we're going to, except I guess we can edit some of the, at least the bad jokes out. So, like I say, I'd like to be slow and methodical, so you will be patient. Here's sort of an agenda that I tried to prepare. It was passed out, and this is reservoir engineering course. That's what it is, really. And very seriously, I'm going to give you 38 years of my experience in 3 days. And if you understand everything that's in the book and everything I say, you've got 38 years experience. You can quit, go into consulting business. And there's a lot here. A friend of mine, Dr. Ramey of Stanford, I'm sure that you've all heard of him if you've been in reservoir engineering or in pressure transient analysis. It indicated to me that even some of the very best concepts in papers, when they're published, it's a minimum of 10 years before they're utilized. The rate time stuff has been out now since about 1973. And they started picking up 10 years ago, but it's about 20 years, and I find it is starting to be used extensively now. That it is a powerful tool, and it was only through the understanding of rate time analysis and performance data that existed in that region that we were able to kind of discover layered no crossflow reservoir behavior and its implications. And again, I hope to go over that with you kind of in detail. There's a lot of potential for increased production and reserves if you understand what's going on. And the first day we're going to cover basically rate time decline. And again, I'm going to try and throw in, while we're going through it, its bearing on layered no crossflow reservoir behavior. At the beginning, we'll give you some of the historical background of rate time analysis, and we'll show you how, for gas wells, you can exactly derive the ARC's equations of rate time decline. Remember, the only reason anybody in this room exists, really, is to make production forecasts for oil and gas reservoirs, or to confirm them. That's why we're in the business. You make the forecast. You're going to see if you're going to develop a field or not, what the economics are. You furnish them to other people, but the drilling engineers, the geologists, everybody is working towards obtaining the data to make a production forecast to see if you're going to develop a reservoir. That's what it's all about. And that's what rate time analysis is about. That there's been a lot of emphasis over the years in pressure transient analysis, but the only application of the numbers that you get is to make a production forecast, or to analyze the data in terms of these wells need the stimulation, and I can increase the production rates a function of time. So this is what it's all about. And you really will never realize the impact of the data that you're getting from the pressure transient until you take that data and make a production forecast. Like if you've ever done any pressure transient analysis, you think, well, if I pick an H of 100 feet or 50 feet, that's going to only change the K by a factor of 2, you know, so that's in the ballpark. Actually, when you're picking an H, you're setting the oil and gas in place. And to make a forecast with half the amount that's there is a drastic change in the economics of a project. So you're not, when you pick an H, you're not just determining K. You're determining the oil or gas in place. And even though it may seem like we're talking about individual wells here in a lot of situations, the whole analysis procedure, the concepts apply to fields, the total field. Some of this will come out that will define or will try and explain what the variables in the ARPS decline analysis or equations mean. Or the D sub I is nothing more than the gas or the potential of the well divided by the gas in place. That's all it is. A lot of engineers, like in the States or geologists, will try and justify the drilling of an infill well or something, and they'll say, I'll pick a 10% decline rate. Well, they're just grabbing that out of the air. You can calculate exactly what it should be if you have an idea of the oil or gas in place and what the permeability is, or if you're going to stimulate. You can exactly calculate that number. It's not an arbitrary number that you grab out of the air. And that's what I indicate here, that we're going to try and develop the physical meaning of the Q sub I, the D sub I, and the exponent B. They can all be calculated rigorously. And I'll show you, again, there's only two fundamental equations for reservoir engineering, and that's the rate equation and the material balance equation. That's all there is. There's a transient period, but that normally isn't really significant. And I can treat a field by an average well times the number of wells in. You know, so everything is very simple. And it was the with the fact I worked in gas at the beginning of my career, the single-phase flow. You can separate all the fuzz, you know, all the snow from a multi-phase flow in reservoirs. And it turns out one of the papers that I published, the isochronal testing of oil wells, and there's an example, at least one example in that paper, which is in the book, that we ran an isochronal test of the initial discovery well of Ecofisk. And the whole concept is that I can express the rate equation for oil wells just exactly like gas wells, exactly the same way, a difference in pressure squared relationship. Production engineers may be familiar. Say, well, we used the Vogel equation, Fetkovich, the answers are very, no, there's more to it than that. It's if you understand that oil wells behave as a difference in pressure squared relationship, the impact of an assumption of a flowing pressure is minimal, okay? A lot of people think it depends what you pick. If you worked in gas, you find out if you square the shut-in pressure of 2,000 pounds and then you square a flowing pressure of 500 or 200 or 100 or 1, the difference in rate when you're working with the difference in pressure squared is zilch. I mean, you can't even plot it on a graph paper. So it's that concept that tells you the impact of some of the things that you might worry about. Engineers have a tendency to worry about precision and accuracy. As a reservoir engineer, I've learned I want to know the answer, like the permeability within an order of magnitude. Is it 1 millidarcy, is it 10, or is it 100? To me, if it's 1, 2, or 3, it's the same answer. Because I can make a lot of reservoir engineering judgments on the basic level of permeability. You know, if you're working in the area, if permeability, say the 1 to 2, even 10 millidarcy, you can't have water influx. Okay, the permeability is too low. So when I look at a pressure cume that may be curved, if you tell me the level of permeability, I'll tell you whether it's a transient, if it's water influx, or if it's layered no cross flow reservoir. this is how you look at performance. That you need to build up certain very simple concepts, and then you can make immediate judgments about the impact or a reservoir performance. And if you listen to everything that I'm trying to say, plus if you read these, or if you look at the overheads and you read the papers, you'll see all this stuff is in there somewhere. It's hidden. And the nice thing to hear somebody talk is that at least gives you an idea of some of the basic concepts. Then it's 1,000 times easier to read it. One of the things I had a tendency to do in writing papers was, everybody's told me out there in industry or in academia, they're too long. Well, they have a lot of concepts in there. They may have the fundamental approach to writing a technical paper is to introduce one concept, okay? A lot of my papers you'll find 10, 20 concepts in one paper. The reason is I worked in industry and I had a lot of things to do, but when you're writing a paper you focus real hard on a particular subject. If I didn't write everything then, I was never going to write it again. So that's the excuse that I have for the long papers and well, the complicated. If I didn't get it down then, it would never be written again. Okay? So you understand where I'm coming from that standpoint. The concept that the B decline on the rate time is a reflection of recovery efficiency or the drive mechanism. I hope you get to cover that. It has physical meaning. The development of the type curve that I came up with where I'd combined the ARPS empirical equations with the constant wellbore pressure solution. And everybody says, but we don't produce reservoirs constant at a constant pressure. Well, in pressure transient analysis or build-up analysis, you don't produce a well at a constant rate either, so don't worry about it. The important thing is it'd be smooth and monotonic type behavior, and you can analyze it without any worries by a normalization process, which is exactly equivalent to rigorous superposition. It took us years to try and get engineers out testing wells to stop going out and keep screwing with the choke. You keep trying to increase the rate. They either come up with a big rate, or they say, well, the pressure buildup will be more accurate if I can produce at a constant rate during the drawdown. The only way I can do that was to mess with the choke. Well, you screw everything up, okay? That's the worst thing that you can ever do on a test is to mess with the choke. Just leave it at a fixed choke and record with the rates and the pressures with time, and you can do a rigorous analysis of the drawdown data and the build-up data. In fact, you'll find if you take the good data, your drawdown data is probably better than your build-up data from a reservoir engineering standpoint. But what we used to do when we'd analyze it, like all the Echo-Fisk wells, you go back, I don't know if the folders are here, but we analyzed every drawdown and every build-up and every bomb that was run in a well, like we'd run 3. We analyzed them all. You can't skip over it, because everything has to make sense. If you analyze the drawdown and the build-up, you get different answers, you got a problem, because you better get the same answer. If you have different rates and different build-up, you better get the same answer. And if you can't do that, there's something wrong. Either with your analysis or there's a new problem to solve. Okay? You go back and look at all of the papers I've ever written. Every single one was written after I solved a problem for Phillips. Never written before. It was after I solved a problem for Phillips. That always came first. So they're all based on field data, and I find out talking to people with academia and even industry, I guess that's one of the things that they appreciate in all my papers. They're all based on field data. And I can guarantee you that the premises and assumptions that are built into many reservoir studies and models, the results are based on those premises, which may or may not be real. And if it don't fit the field data, then something's wrong with your model or your whole concept of reservoir engineering. Just as an example, I'll cover it here, but as an example, every full water drive oil reservoir that I've ever seen has a decline exponent B of 0.5, okay? So I approached a friend of mine and said, hey, I wonder why this is happening. He said, well, I'll set up a model. I'll run it and we'll find out why. We'll look at different relative perms and so on and so forth. So he did, and he ran all these cases, and he said, hey, no matter what I run, I get exponential instead of a B of 0.5. There must be something wrong with your data. Think about that for a little bit. There's something wrong with the premises that are set in running some models. That's the problem. The field data is trying to tell you something. We'll go through a lot of field examples with a detailed discussion of each. You'll see that there are several that come from the Ecofisk area. You'll also see that there are quite a few that come from the States, but it's the whole concept of dimensionless solutions it's valid everywhere in the world. I'm sure you people who do pressure transient analysis, you use the type curve. That's a dimensionless solution, the PDTD. How many of you do pressure transient analysis? Raise your hand. Okay. Yeah, because the other thing, it was the basic understanding of the concept of pressure transient analysis, the type curve and superposition that led to the understanding rate time. Because rate time is if you take the PDTD curve and you just flip it upside down. That's rate time. So there isn't anything new to learn. That's how you make the transition very quickly. That QD is equal approximately to 1 over PD. So everything I know about pressure transient analysis I can immediately apply to rate time analysis. I can take the same data, normalize it. You plot it either as a constant wellbore pressure type of data, and it'll fit that solution. And the same data, you take the tracing paper and you flip it over, and it'll fit the PDTD or the QDTD. So I'll show you an example of that, but you have to understand the implications. That there is really nothing new to learn if you understand a pressure transient analysis. You just apply the concepts. Well, the second day we're going to get into a full day of depletion performance of layered reservoirs without cross flow. And the two good field cases we have come out from the Texas Panhandle. One's a sandstone reservoir, and the other is a carbonate. And don't let it fool you, because it's in the States and it's low pressure, that just applies to the Guyman-Hugon. It applies to the whole world. Carbonate reservoirs, if you start to understand, I talk to geologists about how they're laid down in blanket reservoirs and cyclical. The majority of the carbonate, in fact, I'll make the general statement, all carbonate reservoirs are layered no cross-flow reservoirs. And you should start with the concept of layered no cross-flow reservoirs is the rule, it is not the exception. Start with that, and you can eliminate a lot of potential disasters in reservoir engineering. And I hope by the time we're finished that you realize what to look for in order to identify any well that is backflowing at the bottom of the hole from a production log. Is it undergoing differential depletion? If it's undergoing differential depletion, there's no cross flow, because it can't exist except if there is differential depletion. Okay? Anybody have a problem with that? That's one way of actually detecting it. And you get RFTs on wells, and you go down and you have different gradients, and they're not on the same gradient you have no crossflow. Now, it turns out that there's a very simple way of looking at it, that if I take the ratio of a layer's absolute open flow potential over its gas in place or oil in place, and divide that by, let's look at a two-layer system first, by the absolute open flow of the other layer by its gas in place. If that ratio is 1, they're going to deplete equally. Even though there isn't any crossflow, it'll behave exactly like a single-layered system. But as that ratio approaches, let's say, a number 10, then you're going to have differential depletion, and it could be very serious. So you can calculate this ratio on the back of an envelope to try and determine if it's going to be serious. And we'll show you that the difference in forecast you get is dramatic. In one case, you're going to have a disaster on your hands. In the other case, you might have an economical situation. But you're obligated as reservoir engineers to run both cases, the cross-flow case and a no cross-flow. And I'll show you how to do it on the back of an envelope. I'm going to talk about a two-layer system, but you can convert almost any reservoir number of layers into equivalent 2 layers. And I'm going to also be sort of talking about a single well. A multi-well system is just the average well times n, number of wells, over the gas in place of that layer. And again, you can do this on the back of an envelope. And I'll show you the difference in forecast is substantial. You're obligated to run those cases. We're going to talk about the Red Cave, the Oklahoma Hugoton, and then I'm going to try and distribute some papers after we have talked about some things to look at. You go through a lot of these old papers published in the 60s and the 70s and start to go through it, and you find out the phenomena that we're going to discuss, you'll see exists in those papers. They're layered, no crossflow. One of the main things you can do with a reservoir that's layered, no crossflow, that has the contrast in properties, is you must stimulate the low permeability layers, or you're going to leave a bunch of reserves in the ground. That's the only control that you have. And there's a couple classic papers, one by Shell that was published in the early 70s on a water flood in West Texas. There's a recent one in the Oil and Gas Journal on a reef reservoir in Illinois, where even though you may understand that I've got to get the stimulation of the low perm layers, they found that diversion by balls does not work. The only way you're going to ensure that you get it is mechanically. And I'll point out to you, with the Hugoton field in Texas, Oklahoma, and Kansas, Phillips and Amoco in 1945 were setting bridge plugs between each of the layers and stimulating them individually, mechanically, with a casing and perforating. And we were getting very successful stimulation in 45 before anybody knew about hydraulic fracturing. You know, we got -5 skins in 45. We analyzed the data in 89, and the skins are still the same. No proppants, no nothing. Again, I'm going to hand you out some papers, and I'm going to also hand you out, this is probably going to be the one that is the easiest to look at, because I'd put together these last year. Dave Reese was taking my place on the SB committee, gas reservoir engineering, for the annual meeting, and he got in all the abstracts for last year. I read through them, and you can begin to see how people are beginning to figure out the layered no crossflow reservoir behavior concepts. Right now we have an advantage. We have a technical advantage, I think, in understanding this, and we can make a lot of extra money in the competitive situation in the States. Over here, if you understand it, you can be able to do two things. You have the potential of increasing production and reserves in areas where the low permeability layers have not been stimulated originally. Or the other is to prevent a disaster in development. If you have layered no crossflow, your production forecast under the assumption of layering, even running with models, is going to be extremely optimistic, or it can be extremely optimistic. And the way that shows up is you're going to get a decline exponent B of a very high value. The higher the value, the more precipitous the decline in rate with time. You know, when you're starting t equals 0, exponential decline is optimistic. It isn't pessimistic. In hyperbolic, or the B values of 0.6, 0.7, 0.8, 0.9 are very pessimistic. I'll show you that. And again, it's real easy. You know, even if you're building a model, run one case, a base case, as a no crossflow case. And again, if your reservoir variables are such that you introduce them all into the model and you run it, and it could be that it won't make any difference, but you're obligated to run it. And I hope to get you to understand also that, in my opinion, the industry is wasting a lot of time in reservoir characterization because they're focusing on aerial variation in reservoir property. It's not the aerial that's going to kill you; it's the vertical. And you at least have logs, well logs, you know, to look at there. That again, I hope to show you some examples, and we'll go through the discussions where you begin to understand this. And again, I brought a lot of papers that I hope to have reproduced, but I'm going to pass out a certain amount for everybody to kind of go through and read after the second day, and we're going to come in on the third day and basically primarily work two problems. One on gas, this can be layered no crossflow, and the other on oil that is going to be layered no crossflow, but we're going to look at the potential of infill drilling. And I'll show you I can get identical responses, homogeneous aerially, with layered no crossflow, that they're attributing 100% to aerial variation. I'll get the identical response. Which one is it? Well, well, to me, it's layered no crossflow. And again, you can look at the data. So that's what we're going to try and cover. We'll try and take a 15-minute break in the morning and the afternoon, and I guess about a half hour out for lunch. And don't be afraid to ask questions, again, as we're going along. I'll try and answer them as quickly, but we don't want to delay too long, other than if it's a very important point, we'll take as long as is necessary in order to clarify it. That's a long introduction without actually seeing anything, but this is the first overhead in your paper. How many of you are familiar with these sets of equations, with the ARPs? Okay. These equations were developed by ARPS way back in the early 30s and early 40s. It's the observation of that he was able to take a bunch of field data, and he came up basically with two separate type equations. One's called the exponential, or decline exponent b of 0. It's a very simple equation, and you can see that if you separate it, that you could plot this, the rate time data on a semi-log graph paper with the log of rate versus time, and it would form a straight line. And this was a very convenient equation, particularly before the advent of the computer, is that it was very simple to plot the data on semi-log, and almost everybody in the industry, even up till maybe 5 years ago, everybody was doing their reserves in the States based on exponential decline with actual performance data because it was convenient. At the advent of the computer, though, well, this form of equation was very difficult in order to handle manually, so that's why nobody ever used this back in the early days. The hyperbolic. You can almost show that there's almost no case that you can derive analytically that you can come up with exponential. There's a couple exceptions, and I'll tell them to you now. We'll go through them later just to kind of give you an idea. One, single-phase liquid reservoirs, totally undersaturated, would be all exponential decline. But nobody produces those types of reservoirs that way. They usually water flood them immediately, or they're subject to strong water drive, so you're not going to see exponential there. High-pressure gas. If you get in 5 and 10,000 pound range, gas behaves exactly like liquid. The compressibilities of gas at those pressure levels is exactly like liquid. So very high-pressure gas reservoirs are going to undergo exponential decline. Again, you tell me the pressure level, and I'll tell you what type of decline. Again, particularly for gas. Oil reservoirs with very poor relative perm curves, it gets back to recovery efficiency. If the relative perm is very bad, you're going to produce primarily gas instead of oil. You can get something that's going to look like exponential, like a b-value of 0.1. Difference between 0.1 and exponential you couldn't tell on a plot. And if you get into the low pressure gas area, and if you're tubing limited, because you've put too small a diameter tubing in your well and you're entirely friction bound, the production at the surface is restricted by the tubing size, okay? That pressure drop, or total pressure drop of the system is going to be primarily a function of a friction drop. And your wellhead deliverability curve, back pressure curve, is going to have a slope of 0.5, which is the square root of a difference in pressure squared, just a basic fundamental fluid flow through pipe. And if you have a slope of 0.5 on a wellhead curve, you're going to end up, even in the low pressure gas area, with exponential decline. So these are the basic fundamental things. This is why we plot back pressure curve data for gas wells. You show me the value of the slope of the curve, and I'm going to tell you what exponential decline. We'll get into that some more. Again, the ARPS equation in a hyperbolic, normally the B ranges between 0.2 and 1 was very difficult to handle because you didn't get a straight line on graph paper. So there's a very complicated way of doing it manually. There's an example in a presentation that I'll show you later. We won't go through it other than you'll see how it was done. But the advent of the computer changed things. People started doing regression analysis. And I'll show you from the type curve, there's a big region on the ARPS dimensionless type curve where all of these from a B of 1 to B of 0 all overlay, okay? So if you fit anything in that region, you can get any answer that you want, statistically. Physically, though, it isn't going to make sense that you can't have that value B. It's very important to understand that the limit on B is between 0 and 1, that you can't get a B value in excess of 1. It's physically impossible. What people were doing, though, is like in the States, there was a region, and you're going to get into it here. We've got some of the regions here. Low permeability reservoirs stimulate a good stimulation treatment. The rate time data and transient looks, if you were to try and fit it to ARP's equation, you can get B values as high as 3. It's the use of transient data in the ARP's equation, where the ARP's equation is strictly depletion. It's got to be in pseudo-steady state. Your entire system has to be in pseudo-steady state or depletion for the ARP's equation to be applicable. Any transient data utilized in the regression fit is going to automatically give you a higher B value than if you eliminate it. So you have to be able to identify, and you can do it by the type curve. Log of rate versus log of time, you can exactly determine what data is in transient by plotting it on a log and fitting it on type curve. And to utilize this equation, you'd have to reinitialize the data in the pseudo-steady state period. Okay? Remember, though, that this has got to be in pseudo-steady state. And the Q sub I is nothing more than a flow rate off the stabilized back pressure curve, period. That's the physical meaning. When you start to get in again into the transient behavior, you can have, a lot of people thought that the Q sub I was a rate that occurred in the early production life of a well or field. It's not. Because if you have a low permeability stimulated well, you can have a transient flow rate in early times 3 times the value of the Q sub I that you'd get from the analysis of your data. So there is a physical definition of that. And again, I can relate the B value to the slope of the back pressure curve, and the D sub I is nothing more than the ratio of Q sub I over the gas or oil in place. That's all it is. And you don't grab a number out of the air. You can calculate it. ARP's equation was always considered empirical. In fact, there's some textbooks, modern textbooks out that still say there is no physical basis for the use of the ARP's equation. It's just experience or historical data. And I had my secretary look up herself in her dictionary the word empirical, because the ARP's equation is considered to be totally empirical. And all that says, if it's empirical, it's relying solely on practical experience and without regard for system or theory, that there's no basis other than that's the way it is. Now, I hope before we finish here that you kind of can see there is a physical basis for the ARP's equations. You can define the B and the Q sub I and the D from basic reservoir parameters. Fluid properties, the back pressure curve, the KH and skin, and so the gas in place. I mentioned to you earlier, I think there's been an update. There's been an update to Nin's book. He's out of Canada, Calgary. I think he's in Calgary. Reservoir Engineering Fundamentals is the book. Your production rate decline curves. The original book was in '63, but he's had an update recently, within the past maybe 4 or 5 years, and nothing's changed within there. And he says, when estimates are based on the mathematical or graphical techniques of production rate decline curve analysis, it should always be remembered that this analysis is merely a convenience, a method that is amenable to mathematical or graphical treatment and has no basis in physical laws governing the flow of oil and gas through the formation. And again, I hope by the time that we're finished that you'll understand that that is not a true statement, that there is a basis for it. And don't be deceived and with the idea that, well, we do all our work here in models and so on and so forth. Well, A couple points. The rate time decline even of the field data and the model that you're trying to do to match it, the B value that you're going to get has a physical significance, and I think Mike is working in that area now on some of the LFIS work that he's doing. So you got to match the rate time decline, or your forecast not going to be very accurate, is it? All reservoirs go on decline. We can't produce at a constant rate forever, and we don't have infinite reserves. Now, in my spare time, I used to take time out to read Muscat. To me, he's the father of petroleum and reservoir engineering. It was amazing what he knew and understood in the 30s and the 40s when he wrote his two books, that there's nothing been invented new since he did his original work. But he did it all by hand. A lot of people wondered what he would have done had he come along during the age of the computer. He worked for Gulf in Pittsburgh out at the research. I'm originally from Pennsylvania, in the Pittsburgh area. I went to the University of Pittsburgh, and the head of the petroleum engineering department at that time was Professor Bossett. And he was the inventor of the relative permeability curve. They ran the experiment. He worked with Muscat in Pittsburgh. And I got this out of his book because it's applicable. A quotation from his book: the hundreds of oil fields that were discovered before 1930 and that are now depleted have the only item of physical significance that can be derived from the available records of the great majority of currently depleted fields is the curve of field production rate versus time. This is what we're talking about, rate versus time. The fields were generally produced wide open at maximum capacity with no controls. And this is my underlining in brackets. This is the ideal situation for rate time decline. So we can go back and look at a lot of these old fields, their performance behavior, and these were the types of fields that Cutler and Arps, you'd taken that data, and that's how they came up with the empirical, or at least Arps came up with the empirical rate time decline, based on field data. The reason that Muscat made this statement is he derived the solution gas drive reservoir performance equations, and what he was really doing here was complaining there's no data out there anywhere that he could test his equations with, because they didn't take pressures, they didn't measure gas-oil ratio, they didn't take fluid samples, they didn't core the wells to get permeability. So the only thing you had for literally hundreds of fields, the field performance, was rate time data. And remember, they basically produced them wide open, and I'll show you in a little bit what that means. Arps had made a plot of the cumulative percent of leases or fields versus the decline exponent B, using Cutler's data, and there was about 149 fields. And you have to remember that the original development of the decline curve equation was based on oil fields only. In those days, they didn't even produce gas. It was worthless. When I worked out in the Panhandle, we were selling some gas at 3 cents an MCF. And that was in 1954, 1955. It was virtually worthless. What was happening before that, there was an area in the West Panhandle field, which is a giant gas field with a large gas cap and an oil rim. the West Panhandle field that was discovered in the 20s as oil, and the gas was there, but there wasn't anything that you can do with it. But people were taking the gas and flaring it to recover the liquids out of it only. Otherwise it had no value. They were also using it to make carbon black too. But what he found was that 90% of the fields or leases had B values less than 0.5. This is very important. The maximum value that you can derive analytically or any way, or run models or do anything, the maximum value of B that you can have for a single layered reservoir system is 0.5. Okay, so anything in excess of that is trying to tell you you have a layered no-cross flow reservoir. And this is one of the impacts of understanding with the value of B as a diagnostic tool. And as you can see, for a 0 or even a B value of 0.1, roughly 10% had B values that you might classify as exponential. And I'm going to show you with the use of the type curves and ARP's example in his original paper of an exponential decline was in a region that you could not prove it was exponential. All the B values overlay each other in that region, so people calling things exponential at that time were not really exponential for sure. You couldn't prove that it was exponential. In no case did he come up with a B value in excess of 0.7. And again, you have to realize that there was a period, maybe 10 years ago or so, where a lot of people were coming up with statistical analysis, computer statistical analysis of production performance data with B values as high as 3. And I'll show you later the absurdity of that number is if you take the reserves that extrapolated to, could be 5 to 10 times the original oil or gas in place. That's the absurdity. But said, well, that's okay because we're going to run economics on our production or our projections, and the discount factor in economics is going to take care of that. So they just kind of blew the problem away. They blew it off. That, well, it really don't make any difference. And we'll show you through at least a couple of examples. And when you include the transient data into the depletion data, it's always going to give you a very high B value. And the high B values are trying to tell you it's transient data, okay? And the implication, if it is transient data for long times, that's a classic case for infill drilling. I'm also going to show you that you can get high B values for layered no crossflow. It's a classic case to not do infill drilling. And if you plot them if you look at the data on semilog, you can't tell the difference. If you plot it log-log, you can exactly tell. Is it transient or is it a high B value? I'll show you those examples. I'm just trying to basically set the stage for what you should anticipate during some of these discussions, what you should be looking for. In 1969, Ramsey and Guerrero, I think this was a master's thesis at the University of Tulsa, wanted to see through selecting 202 leases where they judiciously selected them so that there was no additional drilling going on at the time on any of the leases. That'll screw up your interpretation. None of the wells were producing water. And they come out with a slightly different distribution than the original ARPs, but still in no case was there a B value in excess of 1. And what you have to remember, the fields that were produced during that era were produced wide open. So you had no chance of developing any type of supplemental drives. The gas gap expansion, water influx, gravity segregation. Also, when you get into this era, 69, you're in the area of lower permeability reservoirs, hydraulic fracturing, and you start introducing some of the transient data too. See, so but Still, in no case do you have a B value in excess of 1. Well, the higher B values that you're getting here are kind of a reflection of a developing more efficient drive mechanism, because you're not producing them wide open. It gives you a chance for gravity segregation, gas cap expansion, and water influx to develop. Also remember the transient. When we were moving from downtown Bartlesville out to the R&D facility, one of the technicians ran into a report that I think I've got the date on there somewhere. Okay, 1931, and he thought, well, this is an old report. It'd be worthless should he throw it away. And I decided to kind of take a look at it, and I'm glad that I did, because there's some very interesting performance data in here. With these three fields here, we're going to look at with the Mejia, the Wortham, and the Powell fields in East Texas, in the Woodbine. They're all basically full water drive fields. Here's the East Texas field over here, a giant field. You get some idea of the way they produced the fields in those days. Yeah, in March 1931. Well, the Wortham field, in 2 months they drilled 322 wells and basically had them producing wide open. The Powell, they drilled 827 wells in 6 months. The Mejia, they drilled 544 in 3 months. That's pretty rapid development. This information also shows up in Muscat, and the reason it was in Muscat is in the old days there was a lot of controversy about recovery efficiency based on spacing. What's the optimum that you should actually space wells in a given field? So this even shows up in Muscat. But you have to remember, we're looking now at 3 different fields, different size acreage. They've got different thicknesses, different number of wells. Everything's different about the field. Okay, they're all different, but they're in the same general area. They're sort of in the same formation. Well, in fact, they are in the same formation, not sort of. Yeah, this is what the rate time looks like on it. A semilog plot. A conventional way of actually plotting data of the Powell field. It's in the Woodbine on the fault line fields, and look at the rate versus time. One of the things that you should always do in analyzing rate time data is also plot the well count's a function of time. Because one of the things that you have to look at is the period that the well count is either reasonably constant, or if it's not, you have to normalize. Total field production rate divided by number of wells. One fundamental reservoir engineering concept in that is a field at a reasonable high permeability that reaches a pseudo steady state very rapidly. Okay, you can't reinitialize during the transient period. You can only do that in a pseudo steady state period. If it's if you really have a substantial transient period, you have to use a superposition. Again, very fundamental concepts that you can look at all this data and be able to analyze and interpret. Well, if you look at this early data, if you draw a semilog through there, look how far off that you'd be extrapolating your rate time in order to get a production forecast and your ultimate reserve. Also keep in mind, have you ever looked at any enhanced recovery papers that are published, how the primary is always exponential? They'll extrapolate on exponential, and the difference between what they get and what they've extrapolated, they're attributing to enhanced recovery. Do you see the impact? You're attributing a lot of additional reserves to enhanced recovery that don't belong there if the B value is high. Okay? You keep that in mind. And something else, when you run models, I'll talk to you about it with a Guyman Hugo. Once I have the model history match, I can go back and play what if. What if I had produced this field at a constant wellbore pressure? What kind of decline exponent would I have gotten? Okay? Yeah, so you can get a value of B that you could use. You now make a discovery over here opposite, and you say, well, I got to make a forecast. I don't have very much information. You can't build a model. You can use the rate time equation. You got to get a value of B. And say, oh, I ran this model. B is 0.6. That's what you use on your forecast. Okay? Yeah, so you can utilize other approaches like running models in order to help you understand what rate time behavior would look like on that field, even though you never produced it that way, for other applications. We've used this a lot to be able to answer questions on other fields or the method. You can end up with a better method of analogy than this rate time data analysis. Look, here's a plot, rate versus time. With a Wortham field, and it's got a B value of 0.5. That's fantastic data. It all fits with a type curve with a B of 0.5. This particular plot, this is our computer program that they only were sort of displaying 0.0, 0.4, and 1. Well, it exactly fits a 0.5. It's full water drive. ARP's example that he has in his original paper of a hyperbolic is a well with a B of 0.5. When you dig into it, it's from the Arbuckle in Kansas, which is a carbonate, which is full water drive. It's a B of 0.5. You read the case history papers that we have in our case history decline curve paper. If you have any questions, ask Mike, because he was a co-author on that paper. So you have somebody to talk to here. Well, take advantage of it, really. And the Salawati Island fields, the full water drive, reef reservoirs, carbonates, a B of 0.5. If somebody, if you're in an area and say, well, the fields in this area have full water drive, you can use that value B in order to make your forecast. Okay? We got involved in an acquisition in Australia. We've got some property now, and I can't remember whether it was Exxon's model that they'd history matched and they'd run, and it turned out it was basically full water drive. We got the forecast or predictions out of the model and plotted at rate time. It had a B of 0.5. Guess what? Recently, Curtis Whitson took some work that Standing did up at Trondheim on layered, no cross-flow water drive type reservoirs, and I think also homogeneous, using the Buckley-Leverett equation, and when you plot the data log, you get a B of about 0.45. That's close enough. Nobody had ever done any work on displacement. everything that I'm going to be talking to you about here from a derivation standpoint is basically depletion. But I am throwing in the ideas that here's some observed data. And this was the observation that I made, that I asked my colleague to set up a model, and let's see what you can get with regard to if you in some way can reproduce a b-value of 0.5. He couldn't. He said, well, something's wrong with your data. If something's wrong with the premises that you input into your model sometimes, okay? Always keep, don't believe everything that you put into your models. Okay, there's the Wortham field again, plotted on. I'm going to sit down for this exercise. That's the Wortham field, okay, log. That's the Powell. Well, the Mejia, I think you've got a copy of this, but I don't have them exactly overlaid in there. You know, you have to do this kind of individually, but yeah, I could do a better job in that if I wasn't in class. But interesting, they all overlay each other. They're only shifted on the axes by the difference in reservoir properties. You know, this is the whole concept of a dimensionless solution. It also says if I have an adjacent field that I have rate time data on, and I make a new discovery, this is the perfect method of analogy. You know, that this is exactly the way it should behave on log paper. That if I have some of the early production performance in here, I could overlay it on the other field's log plot, just draw the line, fit the data, draw the line, I've got real time, and then I can go and I can read off the rate versus time, let's say at the mid-year of each year, and I've got my production forecast in 15 minutes. How long would it take for you to kind of set up a model to maybe solve the same type problem? You know, these are three different fields. The thicknesses are different, porosity is different, permeability is different, the spacing is different, but they all overlay each other. You have to think about that for a while to understand the implications. And they all have a B of 0.5. Well, we take about a 15-minute break and get back together. And if you have any questions, don't be afraid to ask. I understand, again, you're getting a lot of new concepts here that you may or may not have been exposed to before. Yeah, is that square on the monitor, or? Okay. I have to keep this axis parallel. Trying to demonstrate here is that we're as reservoir engineers or drilling engineers or production engineers or geologists or log analysts or what have you, this is what it's all about. We have to produce a production forecast on all our various projects, and then we run economics and see if things going to be economical, but you know, we also look at trying to improve the production forecast too. So we not only produce one at the beginning, we try and confirm what we've done in the past, or we try and demonstrate that we can improve on what we've got. And generally, I sort of drew this from a gas reservoir engineering standpoint. It's also applicable to oil too, within reason. At least in the old days, there was a build-up period when you drilled your wells, and then there was a constant rate period. And what we're really talking about here is, from a rate time standpoint, is the decline period. And one of the mistakes I made in the original paper was not to include a very fundamental statement that you can't do decline curve analysis unless the well or field's on decline. And what that ended up resulting in, a lot of people were going to the public data systems like Dwight, and they'd start the plot of the log rate time data from the beginning of production. So you ended up that you had the constant rate period included in your time plot. And I can tell you, when you add additional time like that into your rate time plot, it's going to make everything look exponential. And there's an example in here where you try and demonstrate that. So you need to start your t equals 0 for log rate time plotting, at least when it's is on decline, or actually any time afterwards is also okay, if you have enough data to uniquely define the value of B. That's the advantage of including as much time as possible, that you can get into the region on your log plot where it becomes unique. You know, but this you might consider the constant rate period. This is the constant wellbore pressure period. Even though you're going to change your line pressure or your back pressure maybe at some future time. I mentioned earlier there's only two basic equations that you use in reservoir engineering or in rate time analysis, and one is the back pressure curve equation that is shown here either in terms of a delta P or a delta P squared versus Q log is the rate equation, and your material balance, which is either pressure versus Q or P over Z versus Q for either oil or gas. You know, we've demonstrated with our isochronal testing of oil wells that for your solution gas dry reservoir performance, that that behavior down in that region is a function of a difference in pressure squared. Above the bubble point, it would be delta P. Single phase water flow would be delta P. You know, a lot of people use inflow, there's a lot of programs out there that use Vogel's equations for inflow performance. And several also use Vogel's equation for water flow. Well, we'll show that, I don't know if we'll get to show here now, but water flow is a function of a difference in pressure. The oil flow is a function of difference in pressure squared. So there's a different amount of water that you're going to get with respect to oil for a change in flowing pressure, and you have to understand, you know, the difference in flow equations. Delta P versus delta P squared. I show on here what we normally plot for gas wells. We plot the transient data And we can also demonstrate the pseudo-steady state data that there's a shift with time of the back pressure curve from a transient period to pseudo-steady state period. When you get into pseudo-steady state, the back pressure curve is fixed. With depletion, you come down, you just trace up and down this curve. I don't know how many of you use program 7151, the gas production forecasting program. You know, all it takes is input of the variables for a stabilized curve, a gas in place, and it just works back and forth between the rate equation and the material balance equation on a monthly basis to get a production forecast. Does anybody here use that program? Okay. We've included in that program the ability to handle layered no crossflow reservoirs, you know, where there is no crossflow between layers. You can put any number of layers in there. I can tell you now, you know, I hope not to forget in the future, when we're doing the Guyman-Hugueton studies, we're able to make well, there were actually two studies. The first one was a red cave study, which was the beginning of all our understanding of rate time analysis, and that was the constant wellbore pressure solution. The field came on virtually wide open at the beginning against a fixed line pressure. We had the rate time data. So we, through the use of these very simple equations, we were able to figure out it was a layered no crossflow reservoir. And we modified program 7151 to do layered no crossflow forecasting with that program. And then we used the model, and well, guess what? We got the same answers with the hand calculation, the 7151, or the 3D model with layered no crossflow. Important to understand that you could do a lot of your initial analysis with the very simple equations that we're going to present here today. By hand, one well, any number of layers, because every layer is totally independent of each other at a constant wellbore pressure, okay? Every one is completely independent. You can run one layer on Monday, another layer on Tuesday, another layer on Wednesday. You add them all together. The only thing they have in common is the same bottom hole flowing pressure. They don't interfere with each other. You have to understand that concept, because one of the first things almost anybody said, we start getting involved in this, well, what we need is a separate tubing completion for each. It's irrelevant. The tubing doesn't enter the problem from that standpoint. Every layer is independent of each other at a constant wellbore pressure. So you can run them all separately, and on Friday come together and just add them all together, and there's your forecast that you can do by hand, and you can run it in 7151 or the model. You can get the same answer. You got the same answer. You don't have to get super complicated in order to understand what originally appears to be a very complex problem. If you take the back pressure equation, and the material balance equation, you know, for simplicity, you know, again, this bothers people. For simplicity, we're going to assume the flowing pressure equals zero. It really simplifies the derivation. I already told you, you know, if you're going to worry about it, yeah, but I'm not going to flow against a zero line pressure. As a prudent operator, you're going to flow against the lowest flowing pressure you can, and if it's a function of a difference in pressure squared, whether it's 0, 100, 200, or 500, the rate's going to be virtually the same, okay? You have to understand that. And this is the difference between understanding, also when you understand that the inflow performance for oil wells is a difference in pressure squared. It's just not that important. And we ran some examples in one of the papers in here on the volatile oil reservoir in Wyoming where we demonstrate this. It just doesn't change the answer. Don't worry about it. The important thing is, I hope before we're all through, is understanding the impact on the layered no-cross flow behavior. That is big, which I hope to demonstrate. And it's these simple equations. For a two-layered system, it's these variables for one layer, the same equation, I plus sign the other variables for another layer, you just add them together. You can do it by hand. What we have here is an exponential or back pressure curve slope of 0.5. So if I have a performance data on a gas well and it's got a slope of 0.5, I can tell you the B value should be close to exponential. Normally what's going to make the B value 0.5, particularly at the wellhead, I can take the P over Z or the bottom hole shut-in pressure and I can take it to the wellhead conditions, and I have a wellhead curve and a PC, and that's where I'm going to deliver the gas. So it's the slope of the wellhead deliverability curve that I'm interested in setting the value of B. Your QGI is a point on a stabilized back pressure curve. That's all it is. So if you have a KH and a skin from a build-up test, you just take the basic flow equation for pseudo-steady state. You calculate the back pressure. That's the Q sub I. We'll work out an example later where we'll show you how to treat it if the flowing pressure isn't zero. But don't worry about it. Again, this is how you end up with the equations. Very simple equations when you're going to assume the flowing pressure is essentially zero. And for exponential, D sub I is equal to the absolute open flow over the gas in place. That's the initial decline. It's got a physical meaning, and you can calculate that. Get on your early period, you get this from the geologist. Now, I'm going to say a good word for the geologist now. All the years that I was working, I used to wonder why the gas in place I'd get from material balance, P over Z plot versus Cume, was always so much lower than the gas in place the geologists were furnishing us. But when you start understanding layered no cross flow, you find out that the gas was there. We just couldn't see it. And I'll go over an example later of the Ghost River in Canada, where it's exactly the case. All the gas was there. It's just that it was in what you end up, to give you an idea where we're coming from, is if you have a layered no cross flow reservoir where the property is such you have quite a bit of differential depletion between the two layers. When you shut a well in, the pressure you're going to see is the pressure of the more permeable layer. You never see the other pressure. So when you're trying to do a history match on that pressure, you're assuming implicitly that's the same pressure that exists in the other layer, and it isn't true. When we get to the Guyman-Hugoton, which we matched with a model, the Kreider layer pressure was around 100 pounds. The Harrington was 300 pounds. So you're throwing away 200 pounds in your material balance match. And it seems like you're deficient in place, but it's there. And if you can measure that pressure and you include it, you end up with the original volumetric numbers that you calculated from a log analysis in geology. That's one of the indicators that when you have a big difference in material balance in place versus that you get from a good volumetric estimate, it's telling you you have a layered no cross flow reservoir system. And if you ever get into reservoir engineering, it's also the same thing with regard to when you get very low recovery factors. It's also trying to tell you the same thing. That's when you're relying on your volumetric as the original in place. Okay, you have an inverse problem here too. If your volumetrics are reasonably good and you're projecting recovery, a very low fraction recovery, it's implying that you may have a layered no cross flow reservoir system. And again, I'll say it, or I'll try to say it over and over and over again. The only control you have over that is to stimulate the low permeability layer as early as possible, because it's the high perm layer that's going to determine the economic life. So you have to do that early, or you're going to leave a lot of additional reserves in the ground. Is that intuitively obvious? There was a classic case run by Coates a long time ago on optimizing development of a field, and he had an example of a gas reservoir where he had a low permeability region and he had a higher permeability region, and the optimum way of developing the field was inverse to what everybody intuitively. You drill the low perm region first because you have to get that production on early as compared to the high perm, because you need a long a period of time as possible to recover that gas in the low perm region. And I'm going to talk to you about layered no crossflow reservoir, a concept to contrast. That's exactly the same problem if you turn it sideways. From an aerial standpoint, if I have a low permeability region or a high permeability, the concepts of layered no crossflow reservoir apply exactly the same. And the response is the same. The only difference is aerially, two big differences. Aerially, I can measure the pressures in these two regions. Vertically, I can't. Okay? And if you were to plot the total performance of a field that is varying, when I say area, I mean regions, big regions. The total field production of a low permeability region and a high permeability region, when I composite them together, each by itself can have a B value, say, of 0.4. But when I add them together, I get 0.8. And if I analyze, if I plot that first on a field and then say, well, I'm going to look at the wells. If the wells have a B value of 0.4, that's saying that my field response is due to aerial. But if the wells have a B value, let's say of 0.8 or 0.9, then it's saying that it's layering, it's vertical. And that's exactly what we did to solve the problem on the Red Cave. The way we got involved in that problem is we were asked to look at the rate time data by a consultant because there was a lawsuit out in that area. And he said it's obviously exponential. Well, we plotted the data and it turned out not to be. It was a B value of 0.9 for the field. Then we start looking at individual wells, and the individual wells were also 0.9. Playing with the rate time equations, we were finally able to conclude that this is a layered no crossflow system. The only way you can get to B values greater than 0.5 as an example is you have to have a composite system with contrasting properties. Because if the properties are the same, I'll show you later, the denominator of adding them together is the same, and you'll end up with the same B value for each individually. But that's only if the properties are virtually identical. Okay, we discussed exponential, and these are the variable names. We first looked at this and we said, no, it's obvious this QGI over GI. After going down through this equation and defining d sub I, by equating this to the ARPS equation, that's all we're doing here. We're taking this equation, comparing it to the ARPS, and then we're equating the two. I think we do that further in our notes, but I just want to point something out here. As we go through here, the d sub I is 2n over qgi over g sub I, where n is the slope of the back pressure curve other than 0.5. 2n over 2n minus 1 is equal to 1 over b, so I can relate b to the slope of the back pressure equation. So that if I'll either calculate the slope from reservoir parameters where I don't have performance data, or if I have performance data, I can predict the value of B and I can predict the value of D sub I. Remember again that the QGI is on the rate off of the stabilized curve, or pseudo-steady state curve. When I look at this form, I say, wait a minute, I can write this in the same form. The difference here is n equal 1/2. You know, if I multiply 2 by half, it cancels, and that's how you end up where there's a 1 in front of it. But the form of d sub I for exponential and hyperbolic is exactly the same. You can only see this when you put it in terms of a back pressure equation with a slope n. Is everybody following this? Do you see how simple it is? Seriously? We're just working with a rate equation and a material balance equation. And I always like to put equations in graphical form because I can see it. And like the back pressure equation, if I go out and I get spot flows and spot pressures, I can plot the data and I can get my back pressure curve to use with my production forecasting. One danger of using computer programs, I can tell you now, some programs require you to put like a spacing, 640 acres or something like that as input into the program without realizing that the G sub I, what you're doing with that is you're calculating the G sub I and it isn't even based on performance if you have the data to plot a P over Z versus Q. You know, if you're going to use the program, you at least better put in the numbers that fit the gas in place that's indicated by your P over Z versus cum, or even for all, your pressure versus cumulative production. I don't know how many people plot that. That used to be a standard performance plot. Your pressure versus cum, and your GOR versus cum in order to analyze performance of wells. You can see now, again, we've put a physical meaning on D sub I, we've put a physical meaning on a QGI, and we've also put a physical meaning on the decline exponent B. We'll show you later, this is one of the advantages of the back pressure approach to oil wells, and I can do the same thing for oil. I can derive the form of the equation for solution gas driver oil wells or oil fields using the same approach. I sort of preceded myself here, but here's what we did really is take the material balance, the back pressure equation, and that's how we got this equation here, and then we equate this rate time equation for gas wells to the ARPS equation, and I can define 1 over B is equal to this. Okay, this is the exponent. So I can put a B in terms of N, and if I define 2N is equal to 1 over 1 minus B, I can equate the B and the D sub I to this term here, and I can solve in terms of the D sub I. You substitute the 2N, and I can even put it in terms of D sub I is equal to 1 over 1 minus B, the QGI over GI. No. That's where it comes from. Reservoir variable. You know, T equals 0 and I have no performance data at all. There's my gas in place that I can get from geology. I can calculate a QGI from my KH and skin from a buildup. I can get with the B value from the slope of the back pressure curve by including in a reservoir non-Darcy flow and including the size of the tubing at the surface to get a wellhead deliverability curve, and that's the slope I would use. I have everything at the beginning in order to be able to calculate these terms to go into the ARPS equation and do everything in terms of that equation there. I don't have to do it in terms of the KH and skin, you know, real complex equation. That's when I have no data at all, I can define these variables. Okay? is starting to make a little bit of sense how simple it can be, and how these empirical equations have a physical meaning. I can also tell you, like the gas in place, that we're showing it there like as if that's an individual well, but I can also treat this as the total gas in place in a field, and I can use an average well times number of wells n, you know, and do a field forecast. You don't have to look at it, well, this is okay only for one well, but how do I treat a field? The same way. An average well times the number of wells n, or depending how you're doing the averaging, I like to do mine at the wellhead for a lot of good reasons, because of the tubing capacity. You just add up each of the back pressure curves. At the same difference in pressure squared values, you add up the back pressure curves for each well to get a total field deliverability, and that would be what you'd be using there. You know, you just sum them up. At the same difference in pressure squared, you sum up the Q's and replot them, and you're going to get a total field deliverability and also a total field flow that you can use with this here. You know, the advantage here is to be able to get answers in a hurry. If management wants an answer tomorrow, you haven't got time maybe even to build a 7151, or you definitely don't have time to build a model. You can use the same approach for oil. We're primarily talking about gas by adding up several 3240 runs for oil field. We did this to solve the offshore California problem. A high deliverability region that was intensely fractured and a region that was not. We did the same thing on LFISC. We ran the original forecast on LFISC on a program 3240. It was obvious we would be in serious trouble by using the high deliverability region in the crestal area of the exploration well, along with a low deliverability region on the flanks. We ran them as two separate forecasts and add the forecast together, and we got reasonable answers. Otherwise, you're giving a lot of weight to the real high deliverability well to produce all of the reserves, you know, even out of the low permeability region. So this isn't just applicable to gas. We did this back in 1970 for LFISC, the early forecast. Big difference in answers if you'd run it by just using an average well of those two. That would be the same as assuming crossflow. It's exactly equivalent to assuming crossflow. Where the other run was a no crossflow case. And again, the difference in answers is dramatic. You can see how we can go through and equate the back pressure results to ARPS in the physical significance of the term. But this is just an illustration. By the definition of B, in terms of the slope of the back pressure equation, B is equal to 2n minus 1 over 2n. So here's, for these slopes of the back pressure equation, these should be the decline exponents I should anticipate. I can go even further, and I'll tell you, if you got high permeability, the turbulent flow effect is going to be dramatic in a reservoir, and you're going to have a problem sizing your tubing because of very high capacity. You're going to be tubing limited, and your wellhead deliverability and combined the bottom hole and the wellhead, you're going to end up with steep slopes. So you tell me the level of permeability I don't even have to know the exact number if it's high, okay? Well, what's high? 500 millidarcies, a darcy, that's the slope you should expect. That's the exponential depletion that you should be doing to get your projection. And again, remember, you can take these ARPS equations, number of wells, you can look at 5 wells, 10 wells, the average well times n. Make your forecast on the back of an envelope. 15 minutes, you can get an answer to management. There's an easy way also to, you calculate how long you can produce at constant rate before you go on decline. You know, you just take the back pressure equation with a line pressure, you go up the back pressure equation at the constant rate that you're going to produce. You get the shut-in pressure at which it's going to first go on decline. You go to your P over Z plot. You have to determine what the cumulative production would be over that period, and you divide that by the rate, and you get the time. And that's when you'd go on decline. You see that? Low permeability, you're always going to approach a slope of 1. You know, so the maximum value B I can get is 0.5, your single layered system. You know, this is the assumption of a flowing pressure of 0. I'll get into it later. For a normal type of back pressure, you may say 0 is ridiculous. Practically the whole Panhandle area, the West Panhandle field, and now also Texas Houston's on vacuum. And it's been producing since about 1925. There's a couple factors involved. Long time, producing time. That's what you end up when you get in layered no crossflow. If you have a field that has a long producing time, you have a layered no crossflow system. That applies to oil and to gas. And if you go back and look, again, don't get caught in a trap and say, well, this only applies to domestic. It's a fundamental concept, and I'll tell you how it applies to Ecofisk. The majority of the carbonate reservoirs in the past, out in West Texas and even in the Panhandle, were thick carbonate reservoirs or completed open hole. A lot of the early ones were shot with nitroglycerin, or they were commingled type stimulation. What you're ending up doing is you're stimulating the high permeability layer only. The low perms never got stimulated. And what you can do now to go backwards, what they're doing in Borger, I made this presentation out there a few years, and they're making money hand over fist with these ideas of going back to some of these old wells. You're cementing liners in there, you're perforating, stimulating by setting bridge plugs, and they're getting big increases in production. Yeah, so this isn't. All right, how does it apply to Ecofisk? Well, I remember, has anybody ever taken the time to read those thick reports that a geologic task force had put together? They're red and thick, that it'd take you probably a month to read each one. The fundamental recommendation was that Ecofisk should have been completed open hole, take advantage of the fracturing. It should have been cased and individually stimulated. In the early wells, we did do the individual stimulation with bridge plugs. And I'll show you some field examples, some old reports of how a lot of these reservoirs were originally completed in open hole, a commingled stimulation. The shell in that one reservoir found that you couldn't go back and use balls in order to do the diversion. You had them, they used packers or bridge plugs. It's the only way you can get it. And so if you're doing that, you ought to take a look. You need to go out and get the data. One of the fellows in Borger was trying to get management. The biggest well they had producing out there was producing 6 million a day. He knew from other data It was a layered no crossflow. So he kept trying to convince them, let's go in and re-stimulate that well. No way. They weren't going to let him touch it. Well, so they let him do a couple others that weren't as important, and he was able to demonstrate substantial success. They finally let him go back to re-stimulate that well, and they got 18 million a day out of it from 6 million. The biggest producer out there. You know, so it isn't. It's not accurate, and it's a competitive situation. This is the other thing you have to keep in mind. If you don't produce those reserves, and the offset operator understands this, he's going to produce your reserves. You know, every well drains a volume in proportion to its producing rate, even by layers. You know, so if the other guy stimulates, you don't, he's getting your reserves and your early production. It's not just deferred. It's lost forever. I need to introduce into here, here's an example with a slope of 1, different back pressures. Your PWF over 0 is a B of 0.5. It's exact from the equations. If you let the flowing pressure approach the shut-in pressure, like this limiting case here, the flowing pressure to the shut-in pressure is 0.9, it's exponential. So the value of B is also a function of the back pressure. But you know, this is nice from a theoretical standpoint. You say, well, look, you got a problem. No, from a prudent operator, I'm going to operate in this range here. And I'm going to operate as low flowing pressure as I can in order to recover all the reserve. Because if I'd operate this way all the time, I can only get 10% recovery. What we use, I don't know how it shows up on your copy, at a back pressure of approximately 10% of the original shut-in pressure, the B is 0.4. That's what we have a tendency to use for gas wells, that this would be the limiting value of B. And if you get a B value of 0.8, it's telling you something. You have a layered no crossflow reservoir system, without question. As long as you've separated out your transient data out of the problem. And I'll show you when we get to the red cave that when you look at the data of a high value of B on a semi-log plot, it looks exactly like a transient. Exactly. You can't tell a difference. If you plot it log-log, you instantly can tell a difference. You know, so it's a tool. I think Mike is starting to use this as a tool to identify where in LFIS that there could be substantial layered no crossflow behavior. You could literally do this well by well. You can find out where you have no crossflow within a given reservoir with the high values of B. If it's important, remember, you can have no crossflow on a property that could be such that it isn't going to make any difference. But you also have to be careful. I'm going to tell you in advance because I hope not to forget. Be very careful of believing entirely the results you're going to get from core data to do your reservoir description. Because if we had to use from core data to describe the reservoir in the Oklahoma Hugoton, there wouldn't have been any contrast at all between the layers. We had to use pressure transient data, and it indicated that the permeability of the crater was an order of magnitude higher than what was indicated by core data. Big difference in the results that you get. The other thing I'd like to point out is this is kind of, you start introducing the concept of the B value starting to reflect recovery efficiency. You know, remember, every well starts out at the same location. Now, it don't know if it's going to have a water drive or gravity segregation or a gravity drainage or anything until the pressure transients hit the boundary. Every well, regardless of what it's going to turn into, starts off at the same place for a given KH and skin, okay? And the only way you can get higher recovery is to come out at a higher and higher value of B, for everything else being equal. This is, if I'm starting out here, and I'm coming down here, and I extrapolate, and I add up all of my rates, the cumulative recovery for this extrapolation compared to this one or this one is going to be lower. Okay? I originally started to work for Vince Smith in the gas department. I started out in the gas department, and he's published a book by Penwell in 1983. If you're worried about the, well, I'll get to that later. He's got a series of curves in that book, and also the tables that you can plot your own log type curve. This is for an N of 1. His ratio is the inverse of mine. He plots shedding pressure over the flowing pressure, so the ratio out here of infinity would be my ratio of 0. And if you take this data here, this would exactly be a B of 0.5, and you get to approach exponential error. But he's got the back pressure actually built into these curves for a given slope, so that if you'd match on here, in the early days when you've got performance data against a higher line pressure, you could use this type of plot, and when you get your match points off the fit of the type curve, you can calculate Q sub I. From your time match point, you can calculate the ratio of Q sub I over G sub I. If you know the Q sub I, you can plug it in here and you can calculate the original gas in place. You can do the same thing for oil, too. I'll show you later, by the use of recovery factor and a Q off the back pressure curve at whatever back pressure that you're at, you can essentially you can do the same thing. You don't have to worry about a separate type curve. But the advantage of this is this exactly fits a B at 0.5, this fits exponential, and in between you got some type of bastard plot that don't exactly fit ARPS, okay? So the tables are in here. If you want to utilize specific back pressure in an early period, we haven't dropped the line pressure yet to some lower values, you can take this information or these tables and kind of plot up your own log type curve. That's for an N of 0.5. One reason I like to include that, an N of 0.5, this is exponential. At a real high back pressure, you can have an N value less than 0 in the early stages. So that is theoretically possible to have a B value less than 0. Unlikely, though, that you're going to really be operating at this high back pressure. When you're in decline, the object should be to lower your bottom hole flowing pressure to the lowest value possible as early as possible to recover the maximum amount of reserves. That should be obvious, I hope. This is nothing more than with the tables. I'm not going to go through them individually. Just point out that this would be the Q over Q sub I. This would be the dimensionless rate. This would be really the dimensionless time for different back pressures in different values N, and you can construct your own log plot for back of envelope type calculations. You can take these equations in the decline curve paper. You'll see in any type of standard textbook on your reservoir engineering, or you could look in a lot of papers where people think that when you plot, you can make a rate versus cumulative plot, that this is better than rate time. And you look where it came from, they're all exactly the same thing. They come from the same place. A material balance equation and a rate equation, and with a rate cum isn't anything other than the back pressure equation and the material balance equation. You can take the rate time and the cum time, substitute, make the rearrangements, go on through, and you're going to get a rate cum equation. The way it's used by the average engineer is you plot it and you get a straight line, you do an extrapolation. They're making the assumption, well, they don't realize that the slope of the back pressure curve is a half, or it's exponential. So if you think, if you're doing a rate time plot and you're doing a cum time plot, and if you're getting different answers, you should be getting the same answer if you're doing it right. One of the problems, again, people don't realize there's an exponent there and they drop it. So one would be an exponential extrapolation and the other could be hyperbolic, and that's the reason for the difference in answer. You're doing nothing different. There's people that take the ARPS equation and rearrange it and say, I have a new method of getting reserve. You can't. Same equation. But if you put it in a new form, it may be very confusing and you don't realize what you're doing. You have to get the same answer if you're using the same equation, regardless how you arrange it. And this is nothing more, again, than to try and demonstrate to you in a detailed fashion with your back pressure equation in coming through with the material balance equation. It shows you how you can do it from those very two simple concepts. You end up with the material balance equation, and you end up with exactly the same form that you saw earlier, from a completely different approach. Or the rate cum comes from the back pressure curve and the material balance. That's where it comes from. And again, you can see this on gas. You'd never get there if you tried to do these derivations on oil, because you're dealing with relative permeability. This is a continuation of that derivation, and just to show you, if you take the original ARPS equation that is published in his very early papers, take the substitutions for the variables, you come out with exactly the same equation. Exactly. Again, he did his empirically. He used the empirical equation. You didn't know where anything was coming from. That's the whole basis, really, of putting this in terms of the rate equation of material. You can define each one of these variables now that you couldn't do before. And this is the final form. You remember this one up here on top? You saw it with your previous two equations. It's identical. For an n equal half is exponential. There's your rate cum equation. You're not using a different method when you're plotting your data rate cum at all. That you're assuming exponential decline automatically. Now we're going to get into oil well before we get there, again, you go from gas to oil. It's a lot easier. I can write these equations in terms of cumulative oil or cumulative gas. Again, remember, the original equations were developed from oil well data. No one ever derived it in terms of gas well performance. And there wasn't any performance that was available to use on an empirical basis. So you can go on through, and the bottom line is in terms of you got a problem now for oil wells. I can define for gas. I can define a gas in place. We saw that from the pressure cum. But now for oil, my definition of NPI has got to be in terms of an oil in place times a recovery factor. And well, like for oil, you'd have to run something like a Turner material balance. Has anybody ever run 3240? Program 3240, the compositional material balance? Or the Turner material balance? This is the way reservoir engineers used to do their work before models. It's nothing more than a one-cell model. And what you do would input, you'd input PVT data and the oil in place and so on and so forth, but you'd use different sets of relative permeability. A very poor relative permeability curve is going to give you low recovery efficiency. A favorable relative permeability is going to give you high recovery efficiency. So you have to get NPI for a solution gas drive. You have to kind of make a Turner type material balance or a one cell model type of a run, or a recovery factor based on with the API equation that some people say isn't any good, but it's better than nothing, or a recovery factor from analogous field. What I'm leading to is the NPI has to be defined by oil in place times a recovery factor. The gas in place, you can do the same thing. And this is where we get away from a PWF only being 0. The G in the equation would be the original gas in place times the recovery factor, where you define it in terms of 1 minus the flowing pressure over the shut-in pressure, if you're going to ignore Z. You can throw Z in there, but then the G sub I is equal to G. The original gas in place times the recovery factor is going to be G. So if you do the matching, you back calculate a G, you know the P sub F, you can get the original gas in place. But you really have to understand that that's how you make the transition from gas to oil. Everybody understands original gas in place. That's a little different. That's functional relative perm. That's why you do, why it's clear when you do the derivations in terms of single-phase gas. Because you'd never get there only looking at it from an oil standpoint or solution gas drive reservoir. You'd never understand what's going on. So there was a real advantage for me starting off in the gas department. I worked in the natural gas department for about 10 years, 3 years out in the Texas-Oklahoma Panhandle, and then 7 years in Bartlesville. This is oil well inflow performance. This is the Vogel curve. With data off of Vogel, he built a model and he ran a bunch of cases for different types of PVT properties and different solution gas drive reservoirs, and he come out with an inflow performance equation. Q over Q max is equal to 1 minus 0.2 the ratio of PWF over PR bar minus 0.8 times the ratio of PWF over PR bar, that expression squared. When he presented it in dimensionless form, and being in the gas department, we had a dimensionless form of the back pressure equation that we used to size orifice plates when we were running multipoint tests. And when I saw his paper, immediately it became apparent to me that what he's saying is that oil wells should behave just like gas wells. So I went out and got a bunch of data, including some on Ecofisk, and sure enough, when you plot the data up, it plots as a difference in pressure squared. As a back pressure curve plot, the shut-in pressure squared minus flowing pressure squared versus Q. And it's a straight line on log-log. And this is a form of an oil well inflow performance. The slope of 1 is very close to the Vogel equation. So if you use this or Vogel's, you get about the same results as a production engineer. But as a reservoir engineer, I need to do more. In this form, see, I dropped the 1 term, and the coefficient becomes 1 for the squared term, and the other coefficient becomes 0. Now I have a back pressure equation where, like I said earlier, it's not, the rate's not strongly a function of the level of the flowing pressure that I'm going to choose. So that's one advantage that I have in knowing it behaves like an oil well, or like a gas well. Well, the circles, or well, the solid line here are the results out of the one simulation model. The simulation model results that Vogel published in his paper. And these are the match points that he referenced. And if you draw a line through match point A and continue as a straight line, you know, this would be the productivity index expressed in terms of a difference in pressure, i.e. delta P. And you'd indicate that that well flowing at that rate, at whatever flowing pressure that is, has an absolute open flow potential of about 330 barrels of oil per day. If you take his inflow performance equation, which is the dotted line here, say that the absolute open flow potential of that well is about 195 barrels of oil per day. Now, if you take this form of equation and use it, you'd get the circles, and that shows that you would get slightly less. For practical purposes, there isn't much difference in the answer here, but conceptually it says that the delta P squared form equation fits better his reservoir simulation model than his empirically backed out inflow performance equation. You know, so from a production engineering standpoint, well, there isn't much difference. But again, you also see that at different stages of depletion that this curve continues to move. And again, the delta P squared fits all the way. It's a better representation of the inflow performance. If you take the results of his model and the results of a paper published a long time ago by West Garvin and Sheldon of Exxon, the very first computer solution, a simulation computer solution of a solution gas drive reservoir, you end up with exactly the same type of results that I'm going to demonstrate here. To include the effect of the relative permeability shift, you know, the curve would be like this at initial conditions. As you deplete and the saturation of the oil, you start to decrease. The relative permeability effect is going to be that you would have a sequence of curves that would be shifting constantly to the left. Just because of the saturation changes. Okay. You don't have this in the gas well. The relative permeability is always equal to 1 in the gas well. So you don't have that shift. You can approximate that shift with pressure depletion by multiplying the delta P squared term by the ratio of the shut-in pressure at any time to the shut-in pressure, you get the bubble point pressure. You know, you got to go below the bubble point before you start building up saturation to get a shift due to relative permeability. If you take all of Vogel's data that he published, and even that other paper, and you use this form of equation, all of those curves that were shifted